Hello, students. Welcome back to this chapter of elastic waves. In the last session, I have discussed the propagation of the elastic waves in a cubic crystal. So, in this diagram, what you are looking is you have taken an elemental cubic crystal. On this cubic crystal, from this side, one force is applied or a stress is applied from this side, that is side EFGH, another stress is applied, and these two stress are opposite in direction. So, so, so this is the stress acting in this direction, and this is the stress acting in this direction, and this stress is we have written in this way. And since these two stresses are in opposite direction, we are getting a resultant stress acting on this cubic crystal. So this is, as you know, this stress is nothing but force per unit area. So the stress is expressed in terms of force. Actually, this is the stress acting in the x direction, but the component of stresses which are in y direction also acts in the x direction. So this is the components of stress acting in the z direction, its component acting along the x direction. So the net, this is the net force acting on the cubic crystal, as we have studied in the last class. And I have expressed this force in terms of Newton's second law. So this is of the form ma is equal to F. This is the force. And this rho naught is the mass of the cubic crystal, and this dou square u by dou t square is the acceleration or the rate of change of velocity of the cubic crystal when it is set into vibration. So this is the equation 1, and these are all the strain components in different directions. This is in x direction, this is in y component in x direction, z component in x direction, like that. This already I have explained in my last class. And substituting this equation 2 into equation 1, we have got a wave equation like this. As the C11, C12, C4, C44 are the elastic stiffness constants, or they are also called as the moduli of elasticity. And these EXX, EYY, EZZ, EXY, EXZ are the strain components in different directions. So from the basic definition of these, we have written all these EXX, EYY, EZZ like this, dou U by dou X, dou V by dou A, like that. All these things are written. And these equation 4 and 5 are substituted into equation 3 to get a last equation. And this we are calling as the wave equation in the x direction. So equation 6 represents equation for an elastic wave propagating in the x direction, that is in the 1, 0, 0 direction. Similarly, this is for x direction, and similar type of equation we can write for the y direction and the z direction. Y direction means along the y axis. Z direction means along the z axis. So in this way, we got 3 equations, important equations of wave given by equation 6, equation 7, and equation 8. So all these things I have explained in last class. And we have studied the wave velocities in the 1, 0, 0 direction. And it is having the 2 cases. Case 1 also we have studied. So we have assumed this kind of solution for that differential equation. And this equation 9 is differentiated twice with respect to time. And we have got like this. This is important. Students, take note of this because I am going to do this again for another case. So again, this is the equation 9. Equation 9, now it is differentiated twice with respect to x. So we got these things. And equation 10 and 11 are substituted into equation 6. And all other terms vanishes because the terms with respect to y and with respect to z vanishes since the wave is propagating only in x direction. So we have substituted this equation 10 and 11 into the equation 6, and after omitting all other terms, we got this, and simplify, we got omega by k is equal to root of c1 by rho naught. And this omega by k is nothing but the phase velocity of the wave. By definition, velocity of a wave is equal to nu lambda or f lambda. So that is the basic definition. So this omega by k represents the wave velocity, means longitude velocity of the longitudinal wave, which is given by root of c1 by rho naught. And this gives the velocity of longitudinal wave in the 100 direction. Similarly, we have studied second case by considering the transverse wave, and so here transverse wave means the wave will be propagating in x direction, but vibrations will be in the y direction. So that kind of thing will be there here. So that is why this kind of solution we have assumed for that. And same thing is done, means differentiating equation 13 with respect to time twice, and then with respect to y times. So then, and substituting into equation 6, all other terms eliminated. So again, we got this kind of equation. So simplify this and got an expression for velocity. By definition, velocity is equal to nu lambda. So from this, omega by k is equal to root of c44 divided by rho naught. So this gives the velocity of transverse wave in the 100 direction. Okay. So if the longitudinal and transverse wave velocities be experimentally determined in the whole direction in a crystal, we can determine the two elastic constants C11 and C44 by its help. So these two constants, elastic stiffness constants, can be determined from the equations of these velocities. Now I am coming to this topic, today's topic. So in the last session, we studied the propagation of wave in a 100 direction. But now we have to think that the wave is propagating in 110 direction. So that is the difference between the earlier case and this case. And so as a case 1, let us now consider a transverse wave traveling along a phase diagonal direction of a cubic crystal, because this is a 100 direction. So we have to assume that the wave is propagating in a phase diagonal, so that it is 100 direction. And crystal planes and directions I have also studied separately in another video that you can see. And so here what happens? The wave is propagating in xy plane, but its vibrations are along z-axis. Its vibrations are along z-axis. So that is why the wave equation for z-axis will have to make use of. So that means equation 6, 7, and 8, what we have achieved or obtained in earlier general discussion. So these are these wave equations. Equation 6 for x-axis, and y for, this is 7 for the y-axis, and this 8, equation 8 for Z axis means when the vibrations are in Z axis, we'll have to use equation 8. So this equation 8 I am taking here. So this is the equation 8. So this we have to take. Now case 1 again, and the solution of this equation 8, we'll assume that it is of this kind. You can note on here what is changed, this part. It is kx of x plus ky by y is that. So this shows that the wave is propagating in a xy plane. Suppose if the wave is propagating only in x direction, this would be not there. Ky of y would not be there. So that is why this shows that the wave is propagating in the xy plane. And as usual, the procedure is same. You have to differentiate this equation 15 twice with respect to time, and you will get this, because one time differentiation gives what is that, omega into omega naught into e raised to all these things. And when you differentiate again, one more omega comes multiplied by omega naught into e raised to I into all these things. So that you are writing as a omega. It's not W, sorry. It is omega. Or we can write W. W is better because this omega is there. This omega is the angular velocity. This is W, sorry. This is a W. So, dou square W by dou t square is equal to minus omega square into W. I got equation 16. And now differentiate equation 15 with respect to x and y twice in the same way separately. You got like this. Dou square W by dou x square is equal to minus kx square into W. And this minus ky square into W, because this is a partial differentiation. And when you are doing this, dou square W by dou x square, you will be differentiating only this part. And this omega t and ky omega are treated as a constant, and they got 0. So that is why only this much you are getting. So similarly, you are differentiating here with respect to y. So this term and this term is 0, and you are getting only this much. And now you substitute equations 16 and 17 into the equation of motion, neglecting first and third terms because they vanish. So here you can see here, this is with respect to z is there, so this term vanishes, and this is here dou y by dou z, so that term also get this get vanished. So that is why first and third terms vanishes. Only we are left with the second term. So this is the second term, minus C44 into kx square plus ky square into w. After substituting these two, because what is there in second term? Only dou square w by dou x square is there, and dou square w by dou y square there. These values are here. It is minus k square into w and minus ky square into w. These values you are substituting here. This is C44 is a common, and that you substituted. So minus n is common, and this is the LHS, this is the RHS. LHS is this one, rho naught dou square w by dou t square. Dou square w by dou t square value is minus omega square w, so that we have to substitute. We have substituted. So LHS becomes, means equation of wave equation becomes like this, minus rho naught omega square w is equal to minus C44 into kx square plus ky square into w. And we will treat this is important. You assume that kx square plus ky square, this is the propagation constant. Let this be some k square, combining these two k's, new k. I am substituting here. So you are writing this as k square, and this W get cancelled. And what is left is this one, omega square by k square. You take this k square to LHS. You are left with C44 divided by rho naught. Or omega by k is equal to C44 divided by rho naught. Then the velocity by definition v is equal to f lambda or nu lambda. And here this is given by omega by k, and this is equal to so here root has to be written. Slight mistake is there. Take note of this. So omega by k is equal to root of C44 divided by rho naught, because omega square by k square is that is equal to C44 by rho naught. When you take root on both sides, this becomes omega by k. Omega by k is equal to root is missed, root of C44 divided by rho naught. So this is the equation 8 as a equation, as a phase expression for phase velocity, because omega by k always gives expression for the phase velocity. Group velocity is not a group velocity, don't confuse, because we assume that here only one wave is propagating. So that's why there will be only phase velocity, no group velocity. So this above solution shows that there is no propagation in the direction of xy plane, and that the velocity is the same as the given by equation 14, which is velocity in the 100 direction. So this is, when you look at this equation, what is came to know that the root of C44 by rho naught is there, both are constant. So this indicates that there is no wave propagation in the xy plane, and this velocity is also equal to the velocity of the waves, as we have already determined in our earlier case, that is 100 direction. So it will become same. So this is for transverse waves. Now I will consider case 2 for the longitudinal wave. So let us take up the other waves for which direction of propagation as well as the particle motion is in the xy plane. So the direction of propagation as well as the particle vibration, when both are in the same direction, so generally it is called as a longitudinal wave. Transverse wave means x will be the wave will be propagating in one direction, but the vibrations will be perpendicular to the direction of propagation. So that is the transverse wave. And in this case, the wave propagation and vibrations both are in one direction. So it is a longitudinal waves. We are considering the case of the longitudinal wave, and this wave is propagating in the xy plane. So that is the important. We have to think that the wave is propagating in any one phase diagonal, along the phase diagonal of that cubic crystal, what we have considered a cube. The solution for such waves is taken to be of the form like this. So that means u is equal to u naught, this will be there, and v is equal to v naught, this. That means so since the wave is propagating in xy plane, so there will be vibrations along the x-axis and y-axis. So that is why this gives the vibrations or displacement of the particle along the x-axis, and this gives the displacement of the particle along y-axis. So the two equations. And these two wave equations are there for x and y directions. And now again we have to take the equation 6 and equation 7, which I have derived in earlier case as the wave equations for x and y directions. These we have to use. And now this type of solutions we have assumed, equation 19. And now you have to, as usual, you have to differentiate the equation 19 twice as below. So that means once we have to differentiate with respect to time, that gives omega minus omega square u. This how comes? Already I explained in the earlier video. And dou square u by dou x square is minus kx square u, because when you are doing this, y is treated as a constant. This y is treated as a constant. So similarly, dou square u by dou y square, x you treat as a constant, x and the time treated constant here. And here y and time are constant, so only you are getting this much. Dou square u by dou z square is 0 because wave is propagating in the xy plane. So this quantity will come dou square v by dou x dou y, and this is equal to minus kx ky into v. That means equation for v, how you are getting this? This equation for v, you have to differentiate this first with respect to x, then with respect to y. So that is the meaning. So when you do that, you will get this thing, minus kx minus ky into v. And dou square w by dou x dou z is 0 because this whenever this z component comes, that term goes 0. And now substitute all these derivatives into equation 6. This is the equation 6. And you see what happens. So all these things, here it was dou square u by dou t square, you substituted its value. Here dou square u by dou x square value, dou square u by dou y square, and it is dou square v by dou x dou y. All these things you substituted here in the equation 6, and use here u is common, so that you have to minus n is there. So this LHS you write as it is, and this minus n comes here, and u is common, you take u common from these two, and here minus n, this minus n comes here, and these are the stiffness constant and kx, ky, v. So in this way, we got an expression for solution of the wave in x direction as equation 20. And similarly, we have to work out for equation 7. Equation 7 means for y direction. So this here equation 7 is there, dou square v by dou t square. This v represents wave is propagating in y direction. So, but here the wave is propagating in xy directions. That is why its component will be in xy direction. So that what we are working out. So this similarly, this kind of derivatives, you get it and substitute into equation, this equation 7, you will get like this after simplification, just like the equation 20 as we obtained for x direction, we obtain this for the y direction. And now you see for the wave in the 100 direction, we have we will take this propagation constant like this, kx is equal to ky is equal to k into root of 2. So this comes from the study of the homogeneous medium. So we have to set kx is equal to ky is equal to k by root 2. Therefore, those equations 20 and 11, 20 and 21, 20 and 20 means our equations slightly changes. So in equation 20, this kx is there, ky is there, kx, ky. All these things we have to substitute. And this condition we have to put. So what happens? Now the equation 20 turns like this, because kx, ky is equal to k by root 2. So it becomes kx square. Kx square, when it is kx square, so this becomes k square by 2. K square by 2. So this is comes. So that is done. And here also kx, here also kx into ky, kx into ky into v is there. So here also you substitute this condition, it becomes again k square by 2. Here also it becomes k square by 2. That means this one. Here also you substitute. When these two becomes equal, you can take common. Then substitute that value, common value is equal to k by root 2. It becomes k square by 2. In this way, I got the equations 22 and 23 by substituting this condition. And now we have to solve these equations 22 and 23. So we can solve these two by taking a determinant of the coefficient of this u and v. So this I am writing here a determinant, which is the determinant of coefficients of u and v in equations 22 and 23. So these are so for example, this is the coefficient of u here in the equation 22, and this is the coefficient of u in equation 23. So we have written a determinant of the coefficient of u and v. So the roots of this equation are like this. So when you are adding these two, so you have to set equal to 0. So simplify this, you will get omega square rho naught is equal to, means this term you take other side. So simplify, you will get this as half k square into C11 plus C2 plus 2 C44, because this term C44 and 44 this term added, so it becomes 2 C44. And these two, from these two, you set this equal to 0 and simplify this also. So here, since this C44 is here, it is plus, but here it is minus. So that is why C44 term gets cancelled and you are left with this thing only. Omega square rho naught is equal to 1 by 2 k square into C11 minus C12, because minus, it is minus, C12 is here. So C11 is plus. So you got equations 25. So equations 24 and 25 are the roots of that equation or determinant. And the velocity of the longitudinal wave is given by the first root, that is equation 24. As usual, you take this one. Velocity is equal to nu lambda or left lambda. So from this equation, from equation 24, it is omega square by k square is equal to this this divided by 2 rho naught. So when omega by k you write, you take root of that. So in this way, you got an expression for velocity for longitudinal wave. So in this case, the particle displacement is along the 110 direction and is parallel to the k vector. The second root gives the transverse wave velocity, means the equation 25 gives the details of the transverse wave. So is equal to Vt is equal to nu lambda is equal to, from this you simplify again, omega by k is equal to root of C11 minus C12 divided by 2 rho naught. So having the particle displacement along the 100 direction and perpendicular to the wave vectors. So in this way, we got the expression for velocity of an elastic wave propagating in a cubic crystal in a 110 direction. So this is the expression for velocity of longitudinal wave in 100 direction, 110 direction, and this is the expression for velocity of transverse waves in 110 direction in this way. So in this way, we obtained the expression for velocities, elastic waves propagating in a 110 direction in a cubic crystal. So, in this study, both we studied the propagation of the elastic waves first in 110 direction, and later we also studied the propagation of elastic waves in a 110 direction. So all the mathematical steps are given completely and you have to work out. Thanks for listening.